Well, welcome to another episode of CyberTalks. Today we have our new co-host, Martin Hayes, along with our guest speaker, Claudio DeSanti, who is a distinguished engineer with Dell Technologies. He will talk to us more about NVMe security. So welcome everyone. It's a pleasure to have you on the show today, Claudio.
Thank you.
So we're veering away from the normal formatting of our program today, as Claudio has prepared some wonderful slides to illustrate our topic of discussion. We'll ask some questions at the end after Claudio presents some slides. So let's dive right in. And your first question for Claudio, Martin?
Yeah, Claudio. So it's great to have you. Firstly, so I'm really excited. I know you've got some slides to present. Question for me, I guess, is I've been involved in networks and fabrics for longer than I care to remember at this stage, right? I'm counting the years, right? So
yeah.
But the question I have is, right? So I'm a traditional guy. I've been in, LAN, SANs. Generally, never had to touch the SAN. It worked. Left it there. Yeah, I mean, there was zoning and stuff that we cared about on the SAN for security. But why now? Why security? Why security on IP SANs?
I give you the immediate answer. Typical traditional SANs are based on the Fabric channel technology. Fabric channel fabrics are usually deployed in total isolation. They are not connected to anything else. They just connect the host to their storage, and that's it. And this gives the customer the perception that they are safe because you cannot reach them from the outside. This is, in a sense, the reason why security has never been too much of a big topic for customers in the traditional SAN realm. When you are looking at deploying a storage area network over IP networks, this can be just a part of your network. They don't need to be separated infrastructure, something which is disconnected from everything. And at that point, what you get is that security becomes immediately important because that is where your data goes and you want to keep your data integrity safe. And so that's why security becomes of paramount importance when you shift from the traditional scheme to more mainstream IP protocol in order to implement SAN. Just as an example, at the last DTW, and where we presented our NVMe over IP solutions, 100% of customers was interested in security. The question that came was, what about security? Because when you are not anymore in your completely locked and maybe physically locked or constrained environment, then you care about what is going on with your data.
Excellent.
I hope this answers your question.
Great, looking forward to it.
Okay, so let's dive a little to see, given we say why this is important, let's go to the details of NVMe security. So first of all, we'll go through a few slides to see what is the SAN security framework, which kind of threats you can find on a storage area network. Then we will look at the fundamental tools, the protocols that are being defined in the NVMe realm to take care of these threats. And then there will be time for questions to see if you like the explanation. Okay, so this is an example of a typical storage area network. You have some servers that are connected to your SAN, connected to a storage, and you have a management console. That is typical situation. And what is the value of the storage area network? You have some shared storage that you can allocate to your servers on demand. It's not something that is statically allocated. But of course, you want to be sure that each server is able to access its own storage. That is the usual thing. So this association of the proper storage to the proper server is where security becomes important. First of all, which threats you can have. First one, someone can try to access your console, management and system integrity. If that happens, all you're better off, because that is the thing that is controlling all the operation. If your management console has been taken over by an attacker, okay, you cannot do much. Then you have what I said, uncontrolled storage access. Blue storage is expected to be associated with the blue server, but instead the red one is trying to access the blue. And this is something that has to be avoided. Or there is a variant of that which is impersonation, in which the green storage can declare itself, hey, I am blue, so please give me access to the blue storage. And then we can have this interesting character that basically the so-called man in the middle that has access to the network and so can see everything, all the communication that is going on, and maybe can add some communication or change what is going on. So this is another thing to take care, communication access. And finally, we have possible external access to the storage itself. So media access or media theft or that kind of access. So these are the possible threats that you can see here. And that's why we need to have some ways to mitigate at least these threats. On threat zero, system integrity, the way in which this is usually controlled, we have a set of countermeasures in terms of management security. So authentication authorization, we have logging and anomaly detection or secure channel to access your console. But another important countermeasure is so-called system integrity. So you want to be sure that you have hardware and firmware and software integrity checks so that everything that runs on your management console is not tampered, but is what is supposed to run over there. And so preferably, this can be anchored to a hardware root of trust. Let's look at security threat one, access control. Uncontrolled storage access, the way in which this is done. You mentioned the word zoning. Zoning is exactly this storage access control, is the way in which you define who can access what. And so in NVMe, it is called NVMe namespace mapping or NVMe zoning, also in this way. Basically a filter that says, oh, only blue can access blue, red cannot. The variant of that is that it does not prevent impersonation. So green can still declare, hey, I am blue, please give me access to blue. And so to cope with this threat, what you have to do is authentication. So you need a proof of identity. Similarly to when you enter the country after a trip outside the country, you get through the immigration office. You need to give to the immigration officer your proof of identity, your passport. The guy look at the picture of your passport, look at you, say, oh, you are who you are declaring to be. You are allowed to enter here. Please come on in, welcome. And if something doesn't work, you are out. Okay, that is authentication, a way basically for the blue storage to for the blue server to tell the storage, I am the blue server, give me access to the blue storage, and the green cannot do it. Finally, we have communication access. The way in which we avoid issues with access inside the network is having the so-called secure channel. A way to basically to verify that each packet that is sent from the server to the storage is integrity protected using some cryptographic technologies and potentially encrypted. And so you guarantee integrity and confidentiality of everything that is passed here. So this nice character cannot see what is going on, cannot alter what is going on, which is the thing that you want to be sure in order to ensure your data integrity. And finally, in terms of external access, the fundamental way in which this is resolved to avoid access to the data is data at rest encryption. So the data inside the drive itself themselves is also encrypted. In this way, someone gets access to the drives, does not have access to the data. And the way in which this is done is something that can be performed on the application, on the hypervisor, or the storage drive themselves. So, network security review. We saw all this set of threats and how these can be controlled using storage asset control, authentication, secure channel, or data at rest encryption. The rest of this discussion is here on authentication and secure channel. You have any questions so far?
No, so far
Nope.
so good.
Great.
All good.
So authentication, let's look how do we do in NVMe, how do we do the authentication? And here I just compare traditional storage area network technologies such as fiber channel or iSCSI with NVMe over fabrics over IP networks. In the iSCSI realm, we define a CHAP and SRP, but actually only the CHAP protocol has been used. Fiber channel increased the security of CHAP with a different protocol, DH-HMAC-CHAP, and defined other things, but they are never been used. So DH-HMAC is the only one that has been ever deployed for some form of security in fiber channel. Again, remember what I was saying before, security has never been a big request for this technology. Here we define one protocol, DH-HMAC-CHAP, which basically try to build upon the experience of the previous ones to make it even stronger. Then we will look about the problem centralized authentication verification, for which there is no real response for both iSCSI or fiber channel, but we have a specific technology that we defined for NVMe called AV. And in terms of secure channel, iSCSI relies on IPsec, fiber channel has an IPsec-like technology called FCSec, but it's basically not used, as I said, and we leverage instead the TLS 1.3 for NVMe over fiber. So let's start, let's focus here. How does
guess of a question on that, Claudio? Right.
Yes, please.
On the I know we said we're doing fabrics over IP, right? So, but we've been doing SCSI over IP for a long while, right? So the same problem arose, right? You're doing SCSI over a shared network. What's the reason we need to lift the bar so much, right? Because we have quite a few iSCSI networks deployed. Some of our customers do for whatever use case, right?
And that is where some security has been actually put together. Sometimes those iSCSI fabrics has been deployed in isolation. And so that's another way in which people do not have to care about security. But in a sense, that has been one of the reasons why iSCSI did not have so much success in taking over fiber channel. Because in the moment in which people wanted to have, the fundamental problem is every customer wants security. No one wants security administration. And if you don't resolve the problem of security administration on simplicity of deployment and security provisioning, basically deploying security is too cumbersome and it doesn't get deployed. So this is why I will go through what I will go through in the next few slides, is trying to understand how the provisioning problem has been resolved for NVMe.
Great, super.
So how does authentication proceed? A host establishes TCP session with the controller of a subsystem. You have the connect exchange, which is performed to set up the NVMe queue and associate the host to the controller. And immediately after this, we have an authentication transaction in which the host authenticates the controller authenticates the host. Once the two endpoints authenticate each other, okay, we are ready, we can continue. This is the authentication piece, the way, let's say, threat queue in the previous discussion that we had. And how does the DH-HMAC-CHAP work? It's a CHAP-based protocol. So any entity, host, or subsystem needs to be provisioned with a key. And the authentication of the DH-HMAC-CHAP is demonstrate that you know your key. So a controller authenticates a host if the host demonstrates that it knows his own key KH. A host authenticates a controller if the controller demonstrates that it knows his own key KC. And this key is not passed in the protocol messages because the protocol messages are in the clear. What instead the protocol uses is the authenticator sends a challenge C, which is basically a random number. The responder computes a response using its own key and use this function called HMAC, which is let's say a stronger version of a hash function, so a non-invertible function, using the key of the responder as the key, and the challenge plus other things are used to compute the response. And then the authenticator verifies the response. So verifying that if you know your own key is the same kind of logical processing that the immigration agent is doing when it verifies that your passport is really your passport and where you're trying to access the country. So, and this is the way in which it is. And the response verification, how does it work? How can you verify the response? Well, for basic DH-HMAC-CHAP authentication, you need the key of the responder. And so what happens is that the authenticator computes the expected response R prime and then verifies if the received response is equal to the compute response. If yes, okay, you are authenticated. You can go. Otherwise, the communication is interrupted. But what is the problem? This is basically the same protocol that has been defined, except some variation or to make it stronger. But this is basically at high level, the same protocol has been defined for iSCSI. What is the problem? It comes on this slide. Let's consider a fabric 100 hosts, 25 subsystems. And suppose that all hosts want to authenticate all subsystems. My initial provisioning, each host needs to be provisioned with its own key and all the 25 subsystem verification keys. If I add a subsystem, a storage device to the fabric, I need to reprovision all the 100 hosts to add the additional subsystem verification key. Same on the other side of the wire. Initial subsystem provisioning, each subsystem needs to be provisioned with its own key and the 100 host verification keys. And if I add a host to the fabric, I need to reprovision all the subsystems to add the additional host verification key. So in other words, when you are using plain DH-HMAC-CHAP authentication, this is something that is difficult to deploy. There is a lot of administration involved with using this protocol. And this is, as I say, at high level, the same protocol has been used with iSCSI. The reason why it has not been deployed is written here. So how we resolve that? We need, in a sense, to delegate the authentication verification processing to a centralized entity in order to simplify the provisioning of the fabric entities. And this is what the AVE is, the authentication verification entity. It's just an entity, an authentication server that stays in the fabric and that enables to offload the verification, the authentication verification processing through a complete database of identity, key records. In NVMe, each host or subsystem has an identity, which is called an NQN. Each of those is associated with a key. Okay, this AV has this record, NQN, key, per each of the players in the SAN. Now, how does the protocol change when I have the authentication, the DH-HMAC-CHAP authentication with AV? The first part is exactly the same. Again, you authenticate another entity if you demonstrate, if you know your key. Someone is authenticated if you demonstrate that he knows its own key. And the demonstration is the same. The authenticator sends a challenge, the responder computer response using his own key and verify the response. But this time, the response is not verified by the entity itself, but the verification is delegated to the AV. And so what happens is just that the entity controller or host will send a message to the AV, hey, I'm doing this authentication transaction. Is this right or not? And the AV will tell, yeah, that is right, the guy is authentic, or no, it's not. Similar, if you look at the example of the immigration officer, when you enter the country, the immigration officer not only looks at the picture of your passport and look at you, but also scans the passport in its machine that basically verifies with a central database, oh, is this guy a good guy, a bad guy or not? Well, it's something similar to that. In a sense, a central way to verify, okay, everything is going right here. And once I have this thing, how does the provisioning work? Let's consider the same fabric of before. The initial host provisioning, I need to provision just the key of the host and the way to access the AV. And when I add something to the fabric, I don't need to touch any host. I just need to add the additional subsystem key to the AV. Same on the other side of the wire. Initial subsystem provisioning. Each subsystem is provisioned with its own key and the way to access the AV. And when I add a host to the fabric, I don't need to touch any subsystem. I just add the additional host key to the AV. Here is when I put everything together, you can compare the two things. So stated, in other words, what this means is that when we add to the DH-HMAC-CHAP an authentication verification entity, now we make the provisioning scale. We do more. We are very now close to an ideal fabric authentication provision, because your ideal provisioning is, I need minimal initial provisioning, and we are there. I don't need endpoint provisioning updates when there is a fabric change. I need consistent behavior. So once I did this on one entity, the other entities in the fabric can do whatever they want, but I don't need to change anything on the entity I'm considering. And I need it to be automated. Today, everyone wants automation. What does automation mean? It means that there is a protocol that does the work. There is basically software and protocol that does work rather than an administrator. And you saw the difference in what happens with this protocol. If you don't have a centralized authentication verification entity, you have a lot of administration, a lot of manual work that you have to do. Once you add this piece into the picture, now you automated everything. Everything is done through protocols, and that's what customer would like to have. The resulting deployment model is basically you provision your authentication once, and then you forget about it. Even as part of your initial provisioning, you set up your keys everywhere in your fabrics, and then the protocol takes care of authenticating each other. Be sure to cut down any unauthorized access to the fabric itself, because the protocol takes care of it. So that's the beauty of what we achieved here, and the additional piece that has been just standardized, David.
Claudia?
And finally, yes?
I was wondering, since the AV contains all the keys of the fabric, could this be exploited in any way?
That is a very good question. The AV, of course, can be exploited, but is one entity. And so you know where to put your defenses, in a sense. If you don't have it, basically each entity of your fabric is an exploitable thing, because you need to put all the verification keys everywhere. So if one unauthorized access happen on one host or one subsystem, okay, now you get access to all the verification keys because they are there. Here, everything in a single place, and so you may take appropriate actions to be sure that single place is very well guarded and protected from a security standpoint. And so the database can be completely encrypted. You allow access to this database only from the entities that are listed into the database itself and not from anyone else. So there are ways to be sure that you don't access the AV, and in this way, you guarantee the security of the overall fabric.
So I have a kind of a related question to that, right? So I guess in practical terms, this database, does it sit in SFSS? Is it part of a CMD or CDN? And on kind of in addition to Shakita's question, what about redundancy, right? So if the database should crash, right?
Of course, in the moment, as everything, whenever you introduce a centralized entity that is important for your work into a fabric, you want to be sure that you have a proper redundancy for that entity. An important point here is that if you look at the way in which the AV works, that's authentication verification. In operation, the AV database is accessed only in reading. You just need to read the key and use it to verify an authentication transaction. You don't change a key. And so you change the key only when you provision a new system in the fabric. And so deploying multiple redundant replicas of a read-only database is actually a fairly simple thing. And so it's not a problem to achieve whatever level of redundancy that you would like in your fabric in this way.
Okay, cheers.
Okay, let's look at the last piece, which is, okay, how do we guarantee that no one can see our data in flight or modify them? We use TLS, which is a very well-known technology. Every time right now you do a Google search on your browser, you are using TLS. So it's the way in which all the internet traffic is protected from changes or from unauthorized accesses. And we defined TLS 1.3 for NVMe. Why that? Well, it's the latest version of the protocol, so as usual it's the latest and greatest, but fundamentally it is a new protocol in respect to TLS 1.2, which is what was previously used, but right now Google uses as an example TLS 1.3, and most of the situation already in the internet use 1.3. And why that is better? Well, being a new protocol, there are more consistent security properties, better encryption, things that had the security flaws has been removed, and so you want really to be here. And how does it work, the TLS 1.3? rather than starting your communication within a host and a controller with TCP, just TCP, you do first your TCP handshake and immediately the TLS handshake to transform this channel is an encrypted channel, a secure channel. And then everything else on the NVMe initialization process is performed. What is the problem of this? That this TLS secure channel for NVMe TCP is based on pre-shared keys. So in order to authenticate and establish a secure channel between themselves, two entities need to be configured with the same PSK. And each pair of entities require its own PSK. We are back to the provisioning problem. In order to deploy this thing, I need to set up one different PSK per each pair of entities I have in the fabric, which is what I call as a quadratic or an n-squared problem. If I have n host, m subsystem, I need to administer and configure everywhere n per m PSKs. A way to avoid this issue is to use the authentication protocol to help, because upon successful completion of authentication exchange, the two NVMe entities are able to generate an ephemeral share session key. So basically a PSK that is computed on the fly. And then you can do, at this point, the TLS negotiation using the PSK that comes from that share key. The implementation result is that TCP connection begins unsecured, then transition to secured. This is something that is called in literature opportunistic TLS, and is as an example used widely in SMTP. So it's not something that has not been done before. No, it's quite used in the internet as well. And the beauty of this is reduce the TLS provisioning problem to the DH-HMAC-CHAP provisioning problem, for which we already discussed. We have now a solution. So the way in which it works, you begin with your TCP session establishment, you have your connect exchange, you authenticate each other and generate a PSK, and then use this PSK to establish the secure channel. At this point, you are ready to continue. So let me get to the conclusion. NVMe over IP SAN provide today easy to deploy and comprehensive security architecture to ensure SAN data integrity. And as we saw, while provisioning the basic NVMe security protocol does not scale, because as I said, TLS require provisioning one PSK per each pair of entity of an NVMe fabric, and plain DH-HMAC-CHAP requires provisioning verification keys everywhere. The addition of the authentication verification entity makes provisioning of this protocol scalable. We can get to a fully automated solution after the initial provisioning. So provision authentication once and forget about it. And TLS concatenation allows to leverage the scalable DH-HMAC-CHAP provisioning also for the TLS technology for the secure channel business. And this is what I add, in a sense, to present this technology.
Great. Well, thanks. I have one question for you before
Please,
we wrap
Shakita.
up.
Sure.
My question is, with the AVE technology, is this what's responsible for increasing the speed and performance over maybe vSAN or other types of storage technologies?
No, the performance is a completely orthogonal problem over there. This is just a way to make deployable the authentication, so the security piece. Performance of NVMe over TCP, as an example, which is a different problem, whenever you compare this performance to Fabric Channel, is a different problem. Needs to be resolved in different ways, but just to give you a high level hint on the solution and what is the point there. NVMe TCP is a new technology, just came out, and many people, when looking at this technology, look, okay, I look at this as a potential replacement for my existing fiber channel SAN for something that I already know. But fiber channel is a technology that exists since about 25 years. And whenever you are using a fiber channel HBA, host bus adapter, an interface for fiber channel, well, that is something that had a long time to be engineered. It is a fully hardware offloaded solution. And when you look at there, you say, oh, I have great performances. Sure, it is fully hardware offloaded. NVMe TCP being a new technology, we are at the first level of implementations. Oftentimes, things are all done in software, and it's fairly well known that software alone doesn't go as fast as hardware. we need to get at least to the second generation of NVMe TCP implementation, in which then a good piece of the TCP processing can be offloaded to the hardware. And at this point, when basically you are starting to compare apple to apples and not apples to oranges, because you have a similar architecture with both technologies having hardware offloaded, now you can see what is going on.
So you're referring there, Claudio, to the TLS offload, encryption offload?
Well, TLS offload, but also just the plain TCP offload, because of course, if you, again, whenever you are comparing these with a Fibre Channel piece of hardware, okay, that piece of hardware is fully optimized and is able to do all the protocol processing in hardware. Oftentimes, what we're seeing for NVMe TCP just run on your regular NIC and the processor does the work. Okay, the two architectures are different. And so when you compare the performances of two different architectures, well, you need always to realize I'm comparing apple to apples or apples to oranges. That's the fundamental point.
Any final questions, Martin, before we close?
No, I'm all set. No, that was great. It's very informative.
Great. Thank you. Thank you, Claudio, for joining us today. And a special thanks to our audience for joining us. As always, it was a pleasure to have you both join us. If you have questions or comments, feel free to leave them in the comment box below. We'll get back to you as soon as we can. As always, stay safe and secure. And until next time, for the next episode of CyberTalks.